Hey guys, welcome to another video, right? And today we'll be looking at Newton's law of universal gravitation, right? So we all know about Isaac Newton. So Newton actually came up with this law to actually explain that there's an attractive force between two masses or more than one masses, right? Now, this law works perfectly with large masses. And we talk about large masses, we talk about planets, stars, right? So even us as humans, right? If we stand close to each other, there's an attractive force, but that force is too small because of the mass from each person, right? So the Newton gravitational force is based on large masses, right? So we know that every object has mass and these masses attract to each other, right? So based on that, Newton came up with this law that states that the force of attraction between two large masses is that proportional to their product, but inverse proportional to the distance apart, the square of their distances apart, right? So based on that, the force of attraction is equal to G, and this G is our gravitational constant, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And we notice that these M's are capital M's. The capital M's shows the attraction or the focus on large masses, right? So we have the mass of 1 plus the mass of 2 over the r squared. R represents the distance that the masses are from each other, right? So that shows us that if the masses are close together, we get a force that is great, right? If the masses are further apart, then we get a force that is becomes less, right? So if you focus on our solar system, right? So we know that the sun is directly in the center of our solar system, right? Then we have Mercury, Venus, and Earth, right? Now, these are large masses, right? And these have an attraction to our sun, right? So because of those large masses being attracted to the sun, right, the distance that they are determines how the attractive force is. So Mercury has a greater attraction to the sun than Venus. Venus has a greater attraction than Earth, right? So these two planets have a greater gravitational force than us here on Earth, right? Because their distance to the sun is smaller than Earth's distance to the sun, right? Now, the gravitational field, right, just like electric field where there is a region around a charge that a force is being felt, the same applies for gravity. So gravitational field is that region around a mass where a force of attraction is being felt, right? So in that case, we can find G, and this G represents the gravitational field strength, right? So the gravitational field strength is equal to the gravitational constant, which is 6.67 times 10 to the negative 11, times the mass, right? And this mass is the mass of the object that you want to find their force for, over r squared. So r now is your radius of the mass, right? So this r represents the radius of the mass. This r represents the distance between the masses. So your gravitational field strength is the force per unit mass, right? So what that is, because we know this value, right? That G is equal to 10, and it shows that it's 10 Newton per kilogram. So for every 1 kilogram where there is a 10 Newton force being acted on that object, right? So that's what this value means. So every 1 kilogram of an object, there is a 10 Newton force being applied to it, right? And then we move to an example of using this equation, right? So we say that the mass of Earth is 6 times 10 to the 24 kilograms, and its radius is 6,378 kilometers. What is the gravitational field strength of the Earth's surface, right? So we know that the gravitational field strength G is equal to capital Gm over r squared. Now the G, as we say, is a gravitational constant. the mass of the Earth, 86 times 10 to the 24, over the radius of Earth, which is 6,378, and we notice it's kilometers, so kilometers times 10 to the 3, which is multiplied by 1,000, right? And then we square that because it's r squared, right? So when we calculate this, we get a familiar number that g is equal to 9.8 meters per second squared, right? So our gravitational field strength as well tells us the rate at which objects will fall onto the surface of the ground, right? Now, there is a mind-blowing question. If you have two different masses, is it possible for it to have the same weight while in Earth's atmosphere? Alright, so I want you guys to leave your comments below to give yes or no, and just a simple explanation. Do you think that the two different masses can have the same weight while in the same Earth's atmosphere, right? So anywhere in that Earth's atmosphere, can there two objects be, right? So they can have the same weight, right? So they don't have to be in the same location, but they have to be within Earth's atmosphere, right? So leave your comments in so I can see what you guys think, all right? Now let's look finally at weightlessness, right? So this seems like just a made-up word. How can something be weightless, right? Because remember, weight is given by mass times gravitational acceleration, right? So everything on Earth has mass and gravity is always present. So how can something be regarded as being weightless, right? Now let's examine, you are in an elevator, right? So you're in an elevator and you have a balance, right? And you're measuring the marker, right? So you're measuring the marker in the balance while the elevator is steady, right? Now, when the elevator is not moving, you're going to get the true reading of the weight of your marker, right? So let's say this marker is 5 grams, right? So that's when the elevator is at rest. Now, if we're supposed to get the elevator moving upwards, right? Do you think this value will still remain, that the weight, that the weight of the marker still be 5 newtons, right? So if your answer is no, then you're right, because this 5 newtons now will change. Why? If the marker is going up, it's being acted against now, so you're accelerating the object upwards, right? While there's a acceleration going downwards. So remember, force is equal to ma, right? So once you have acceleration, there's a force. So we're applying a force up while the force of gravity is going down, right? So those two forces, right, will cause the object now to change its weight. But do you think it's the same if the elevator was going down? It's the same, right? So in this case, if the elevator is going down, right, then the weight also changes. But what if the elevator string got cut, right? And now the elevator actually is moving at the same acceleration as g. So that means at g would be the a, which is 9.8, right? So if the elevator is accelerating at 9.8, meaning it's only falling because of gravity, if by any chance, right, I'm in the elevator and I allow the marker, I'm here with the marker, and I let go of the marker actually will maintain that same position, right? And that position creates that the marker is weightless. So if the marker is still in the the balance, it will record a reading of 0 newtons, right? And that's because the the net force on the object is 0, right? But in the elevator, right, I am going down at the same acceleration while the marker has the same acceleration as well. So if the marker was here when I released it, it will remain here because we are both going at the same acceleration. If I was here, if the marker was down here and I decide to let go, then the marker will maintain at this until the elevator stops or until one of us actually remove from being that acceleration as g, right? So until the elevator stops or hits the ground, then both of us, myself and the marker, will actually maintain our position, right? And at that point, we both are noted as being weightless, right? So that is the principle of what weightlessness is. Alright, so thank you very much, guys, for watching another lesson. I hope you understand something about Newton's law of gravitation or universal gravitation. Alright, and see you guys next time.